Okay, so I'm recording now. Self-marking, okay, so not available for self-marking. So let me check again, maybe at 3 o'clock. Only maybe you can only do this at 3 to 5. 3 to 5. Try again. Regular class. I don't know what had happened though. Let me check again. I click on this, and this is the password. Now feedback to me if you cannot can already, fine, so it's good. So I am already begin the recording on my screens. People are still coming in. So we have 18 persons. Okay, 19. So for those latecomers, you just take your attendance on the screen. Okay, so let us wait for a while. Okay. Okay. 20%. Okay, 22. Okay, so okay, people are coming in. Admit. So this is attendance sheets for those who wants to take attendance. Okay, so you can at least see my face on the screen. Okay, half of my face. Maybe upstairs a little bit. Okay. Okay, so it's a 3:03 now. While waiting for people to come in, we will begin our lecture. It seems like we always have to drag on for many minutes before we can formally begin our lecture. Okay, so today we are going to talk about a new topics. Let me go back a bit. So you can click on the link to new lectures, which is on part 8. So we're going to talk about first order differential equations. So you click on it and open it. Now this time we are hosting the file onto Google WebEx. So when you click on it, you see these sort of things. So what you should do is that you should open Google Collaboratory. So I suppose in order to use the Google Collaboratory, you have to register for a Gmail or Google Mail or something like that. So just register one if you cannot open it. So when you click on it, now there would be some problem if you are using the Internet Explorer from Microsoft. So Microsoft may not allow you to open it. So what you do is that you open the link in other web browser. For example, in the browser like this one, I just cut and paste into the Firefox. then Firefox will be able to open the link from this link, okay, part 8, and open it in Colab. So the good thing about the Colab is that you can actually edit it. You can edit on the screen. If your web page is, if a line is large enough, you can actually run the code on the on your web browser directly without downloading it. But of course, what you should do is that you should also download the files into your local hard disk, so that you can not only run it on the internet browser, you can also run it locally on your computer. Okay, so if there's any problem, just go to the file and then save a copy. I think you can just download IPYNB into your local file, or you can just run it, right? So you look at this file, you can actually run the file. So just double click on it. So you go to this. So to run it, you just press Shift Enter. Okay, for example, you see this is a code, right? So it's a code that I have written. So you can just press Shift Enter, or just click on this button you see on the screen. Then you click on it, then you'll be able to run it on the spot. Okay, so that's a good thing about the Google Colab. But I expect that you should download the Google Colab into your laptop. Then you can manipulate it. Okay, so whenever I change the files on the screen, then the file will also be changed on your screen as well. Wait, I think people are asking some questions. I have to admit people in. Okay. Yeah, it is recorded. I am not recording it onto the WebEx, but I'm recording it on my local hard disk. So you can see that on the right hand side you have a screen. This screen is my local web page. I think this is called I think I'm not recording in WebEx because WebEx the resolution is very bad. So I record it using my local recorder that you can see, or maybe show. So when you see this. Okay, so I'm recording using this one so that the record is more higher in resolution. Okay. Now today we are going to talk about how to solve a first order differential equations. The idea is very simple. If I give you a first order differential equations, how would you solve it? So suppose that everyone knows what is the differential equations and then integrate a first order differential equations, right? So basically a differential equation, first order differential equations is just is in this form, right? So given any differential equations, you can always integrate. So this topic is requiring you to understand what is a differential equations, and then how to solve the differential equation by integrating it. So you need to know what is a first order differential equation, and you need to know what is the integration. Now all of this has been exposed to you in your secondary school as well as in your first year, especially in the class of ZCE 110. So let us go through and browse through this quickly and see what we are going to expect for this lecture. So the idea is very simple. I give you a functions in terms of a differential equations, and then your job is to perform an integration and give me the solution. So we're going to go through some exercises and how are you going to use Python to do this sort of integration. So there are some exercises, and then we are going to show you some examples of first order differential equations, and then how to program it. The difficult thing is not in solving the first order differential equations with a single variable. The more difficult thing happens in solving a simultaneous equation. So if I give you two differential equations simultaneously, how are you going to solve it? For example, this sort of situations, you have three differential equations, first order. What is the solution? What is the function of h? What is the function of I? And what is the function of v? So you are going to give me the solution by printing out the numerical value and then give me the function. So basically, I give you a first order differential equation and then use Python to solve it numerically. After solving it numerically, you have to plot it out, okay, so that you know how the function looks like. Okay, so it's kind of simple. So to remind you what is a first order differential equations, please look at the screen. So I'll try to make it larger so that you can see it better. Okay, so on the screen you should see that I try to explain to you there are many differential equations in your physics class. Many differential equations, you have seen it for many occasions. The most simple differential equations is the first order differential equation you have seen, which is the free fall under gravity. Okay, so in your secondary schools, you learn about, okay, let me go back to this one. Okay, let me call my own file. I think it will be better for me to run on my own files back. Okay, so let me open this. So this is the same file as you are seeing on your Colab. So when I change these files, you would see some changes as well if you refresh it. Okay. Okay. Let me make it larger. I should do something. Let me save this as okay, so let's come back again. Now, if you have a object which is falling under the gravity, what is the equations that govern them? So you memorize all your formula, right? The first year, second year, secondary schools, that when object falls under gravity in your 101, especially you learn that the velocity v equals to u plus at, right? In this case, v is the initial position or initial velocity where the object starts to begin at time t0, and then it falls under an acceleration. So in this case, if it's fall under the gravity, then the acceleration is just g and it's falling downwards. Okay, someone who are out there, if you want to say something, you can. I think Zaim Shami, maybe I will switch off your mic. Okay, okay, fine. For those who have not switched off your mic, maybe Eliana. Okay, I'll switch off your light unless you have something to say. Norly, Eliana. Sorry, I don't hear anything from Norly. Norly, are you saying something? Okay, now I'll switch off the mic, okay? For you. Now, in case you need to, you can switch on your mic. Okay, so let's just continue. So the equations that governs the free fall is dv y dt equals to minus g. So basically it says that there are a variable. In this case, the variable is the velocity along the y direction. So it says this is the vy is a variable that describes the velocity along the y directions. And how does this velocity y directions change with respect to time? So dv y dt is a mathematical equation that describes how the velocity of Vy change with respect to time. And it says that it's equals to minus g. It means that the rate of change of the velocity along the y directions with respect to time is equals to minus a constant, which is minus 9.81. So this is nothing but just a first order differential equations. Okay, so it's first order because you differentiate the velocity functions Vy once. And you also have another first order differential equation describing not the velocity along the y directions, but the y position instead. So for a object which is moving in one directions, you have three interested quantities you want to measure: velocity, Vy, the position, which is the v, and also the accelerations along the y directions. So Vy is the variable that change with time. Y is the variable that change with time. There's another one which is a along the y. So the ay is just nothing but minus g. Okay, so this minus g is the accelerations along the y. So each of these quantity, that is the dynamical variable, we call it. Dynamical variable here refers to quantity that change, that describes the motions and it change with time. So basically it means the velocity, the positions, and then the acceleration. So each of these differential equations that you see here is a first order differential equation that tells you how the velocity change with time. And this equation tells you how the position change with time. So you need only two equations to describe the motions of this falling object. Since this is 1D, right? It's 1D. So you talk about the y positions, and you are interested in basically two quantities, which is the position and the velocity. So in this case, the accelerations is not as important. Okay, so you need to know what are the equations that governs the motion. That means what are the equations that governs how the velocity change with time and how the position change with time. So these are the two equations, and these two equations that you memorize since the first year, since Form 6, whatever. It's a set of equation of motion, right? You have two equation of motion, one for position, one for velocity. It's always come in pair, okay? The velocity and position always come in pair. Sometimes is the position and the momentum. Momentum and velocity are the same, right? So momentum is just velocity times the constant, which is a mass. So you describe the state of motions for a dynamical system using two very important variable, the position and velocity, or position or momentum, either one would do. Okay. So you need an equations of motion that describes how this position and velocity change with time. And this set of equations is called equation of motion. So generally, if you have a system where things are changing under the influence of a force, you want to know how the position change with time, you want to know how the velocity change with time. So you need an equation of motion. So as long as you know the equation of motion, you'll be able to predict or describes the behaviors of the dynamical system. Specifically, you would be able to predict or describe how the position change with time and how the velocity change with time. Right? See, this is what you learn physics for. You learn what are the equation of motion that governs the dynamics of a system. Then you solve it. You solve it meaning that you want to know how the velocity change with time and how the position change with time. So if you know how v change with time, velocity and the position change with time, then basically you know everything about how this dynamical system change with time. And that is our purpose, right? You want to describe the system, and then you want to know how to predict it and calculate it. Right? So this is what physics is doing. So we have a lot of equation of motions in physics, and most of these the equation of motion are expressed in terms of a differential equation. For the simple case of a gravity 1D that describe the position and the velocity, you have these two first order differential equations. Later on, we will be seeing that other than first order differential equation, more generally, the equation of motions for a dynamical system in physics mostly is not described in first order differential equation, but second order differential equations. Why is that so? Because You know why is that? That most equation of motions in physics are described in second order differential equations. One of the very simple reasons is that Newton's law, F equals to ma, the right hand side, a, right? A is an acceleration. Acceleration is second order derivative of the position with respect to time, right? So principally, mathematically speaking, Newton's law is a second order differential equations in time, right? So if you were to use the first Newton's law to describe the dynamics of object, then the equation of motion that you derive from there is a second order differential equations. So for example, when objects are colliding with each other in 2D collisions, so you can write down the conservation of momentum, and you write down whatever equations that you use to describe the collisions of the dynamics between particles. You will end up with a second order differential equations. So we always encounter many first order, second order differential equations in physics. Therefore, one of the things that you will learn in ZCE 111 is to handle these second order differential equations and solve it. You may not use it if you are a first year, second year student, but if you go to higher and higher level, when you start to do modeling, you would encounter many equations that will tangle up together, which is much complicated than what we see here. So this course will give you a chance to handle commonly seen first and second order equations in physics. So we will pick up a few classical examples. So the first example for first order differential is always the gravity, right? Because it is first order and everyone are familiar with it. So you memorize all the formula: V equals to U plus AT, like Y equals to whatever UT plus half GT square, V square equals to U square plus 2AS. And so these are the four equations that describe the kinematics of the motions of object, right? So all these equations that you memorize in your first year in your primary school, in your Form 5, Form 6, matriculations, first year 101, these are all the equations that are the solutions to the first order differential equation that is highlighted on the screen. Okay, so you are supposed to know how to solve this, and you are supposed to know what are the solutions to this, because you have memorized all this formula. The four kinematic equation is the analytical solution to the equation of motions for this object falling under gravity, and these are equation of motion expressed in terms of first order differential equation. There are many other examples which I'm going to talk about here. For example, if you have a more complicated situations where the object is falling in gravity but experiencing a drag force, so you have dv dt equals to mg minus kv. So I think these equations is slightly different than that, in the sense that for this equation, the first one that I highlight on the screen is using a coordinate system which is opposite to the formula for this. Okay, so I think this one, it assumes that pointing downwards is positive, whereas here pointing upwards, object which is pointing upwards is a positive. So because of the difference in the coordinate system, so you see that here dv dt equals to plus mg, whereas here dv dt equals to mg only. I think there is some mistakes here. dv dt equals to minus g. I think this is correct. I think there is some mistakes here. So I think this is not dv dt equals to mg. I think this should be opposite. So let me correct it on the screen. So when I correct this, you'll be able to see the same correction that happens in your collab, because these are two things that is changed. I think this is k over g, k over m g. I think that is more accurate, or maybe not like that. Mg gk. I think it's like this. M times dv dt equals to g minus mg minus kv. Yeah, I think that is more accurate. Now the reason of the error is that the dimension is not correct. So this should be m dv dt. M dv dt would have a dimensions of a force, right? So dv dt is a dimension for the accelerations. So if this is the case, then I have to make sure that the dimension is correct. So m times dv dt is the mass times accelerations. So the right hand side should also be mass times accelerations. So this mass times acceleration is in unit of is a unit of force. Okay, so then yeah, I think this makes this more accurate. So let me save it. Then after I save it, in a moment you will see the same corrections will occur in your page. So I just add in a m here. Okay, so I think that should be okay. So if you have an object that is falling under gravity, and experiencing a drag force which is proportional to the speed, right? But the force is opposite in directions to the velocity, then you have this minus kv term comes in. So this is an equation of motions that describes the object falling under gravity with a drag force, and we have seen this also in the earlier part of this lecture, of this course, right? But we don't really solve it very rigorously. So this is the first order differential equations. How do you solve it? Okay, so you have seen this, and in order to solve it analytically, it could be quite well, a bit complicated, but not as complicated. So we'll see this example later on, and we'll see how to solve it. But mind you, if you set the k go to 0, k describes the drag force, right? So if you have an object that falls under gravity with a drag force, then you arrive at the terminal velocity. But if you set the drag force to be 0, as like it's falling into a vacuum, then you have m dv dt equals to mg, which is just equals to these situations. Okay, so this is a general situation, a general case, than the free fall case. Okay. Now, so this is the second example of a first order differential equations in physics. Now, I keep on telling you a lot of these things you may have known already a long time ago. I have to keep on telling you because I want to remind you what you learned in physics, what you learn in the mathematics, what you learn in ZCE 111, the programming, is actually trying to describe the real world. Right, so the real world object falling is governed by a set of equations. So if you, when you look at some equations and then you can appreciate that well, these are the equations that is describing our real world, you appreciate what you learn, right? So if you do not have this kind of appreciation, you just keep on telling, this is just a formula I've memorized and then that's all for my exam. You are missing out a lot of opportunity, right? So these equations are not just equations for you to memorize. It just simply means these are the equation of motion that describe real thing in a real world. In order to use this knowledge to predict their movement, you have to appreciate the significance, or you have to appreciate the meaning, the interpretation of these equations. Okay, so okay, that's all I want to say. Now, another very important law that you see is, I think they call Beer-Lambert Law. Now, this is purposely meant for those medical physics students. Like most of you are medical physics students, I suppose. So, medical physics students, what you learn is you learn, say, radiations, right? Radiations, gamma ray or gamma ray, beta ray. So, when radiation goes into a tissue, what happens is that this gamma ray will interact with the tissue. Then the intensity of light when it passes through the tissue would drops when it penetrates further and further into the tissue, right? So the dropping of the intensity of a ray of gamma ray, when it penetrates through a distance of z in some material, it will decay exponentially. Okay, so this is called a Beer-Lambert law. So the Beer-Lambert law actually comes from a first order differential equation. What it says is that if you have an intensity of light going into a materials within some depth. Z here refers to the depth of the object. The more you penetrate into the object, that means the larger is the Z that the light pass through, the more it will decay, right? So the larger is the penetrations into the object, which is the larger is Z, then the decay would become larger. So this is basically an equation that says the rate of the decay of the intensity with respect to Z is proportional to the amount of Z it goes through. It makes sense, right? So initially the object intensity is very high. When it passes through some object, the distance of Z, then it will drops, right? So the more you penetrate through the Z, the larger is the dropping, or the rate of dropping of this intensity with respect to Z. So this says the intensity rate of intensity drop is proportional to the depth it penetrates through. The negative here means that the rate is dropping. Okay, if this is positive, that means the rate is increasing. Alpha is a quantity that is characterized by the material itself. So different material have different alpha. Some material allows object to penetrate through without decaying too much in its intensity. Some say very dense object, when the ray, gamma ray or beta ray go through a little bit, then it would drops a lot. So for that kind of object, which is normally very dense object, then alpha will be larger. For those tissue, then the alpha will be larger, right? So you have this idea called the skin depth. So that means if the alpha is larger, then the skin depth is smaller, right? It means that the stronger is the object, the denser is that, then the penetration would be lesser, right? So this is a law that you will encounter again, not only in particle physics or theoretical physics, but in medical physics. So these equations that describes the penetrations of a ray into some materials, such as your tissue, is given by this first order differential equation. How do you solve it? Now we have actually solved this before, so we are just saying it again. Now radioactivity is the one that actually we solve it. But you look at these equations, the radioactivity, it means that the rate of the decay. So I think this is the, so dN dt. I think that this is an error again. This is a typo error. dN dt, not dN d tau, is n over tau, is n over tau. Yeah, I think that is more accurate. So dN dt. dN dt I think that is the equations of how an object decay in a radioactive setting. So it says this tau is a constant. So dN dt here means the amount of radioactivity change with respect to time. So dN dt here is the rate of change of the amount of nucleus with respect to time. And the more n on the right hand side, that means the more amount of radioactivity materials remain in the sample, the larger is the decay rate. Now this is very similar to these statements in this law that we mentioned, the Beer-Lambert Law. Here is a rate of change of the intensity with respect to the penetration, but on the radioactive side, it is a rate of change of the nucleus remain with respect to time. So here you have a Z, here you have a time, but either case, either this equation or these equations, the rate of change is inverse, is proportional to the negative of the penetration, or proportional to the time. I think, is it? Maybe I have to check. It doesn't look very accurate to me though. dn dt, yeah, I think these are very much the same. Okay, so here I is replaced by n, and then here you have a z on the right hand side, but this one on the right hand side you have an n. Okay, so alpha is replaced by 1 over tau. Okay, so I think I have to make some corrections to these statements. Maybe there is some mistakes here, but doesn't matter. Okay, this is not important. Okay, the important is that we have a formula that describes the nuclear decay is also a first order differential equation. So we are not going to talk about this one here in the lecture, but maybe in your tutorial. I'm sorry. Okay, so we have spent about not quite a lot of time to describe the theory. Then standard equations is the harmonic equations of motions. So you have a pendulum which is changing with the position, right? So the more displacements in the object from its equivalent position, then the larger is the restoration force. So this is an equation of motion. M dv dx on the left hand side describes now a pendulum. The force of it, right? The force is the change of momentum, linear momentum. Well, now, okay, so maybe the derivation for this simple harmonic motion is not shown here, but you should be able to figure out what it means by this. So anyway, this is equations of motions that describes how the velocity of a pendulum. So you have a pendulum that's changing with time and also with position, where x is referring to the displacements of the pendulum from the equivalent position. So the more you displace the pendulum from its equivalent positions, then the larger is the restoration force. Okay, so this refers to the restoration force of the pendulum from its equivalent position, and the left hand side is the rate of change of the velocity with respect to position. Remember, you have pendulum. If the pendulum is swinging to the furthest until the end, for example, then it will stop for a while. When it comes back to its equivalent positions, the speed becomes maximum, right? So the speed of a pendulum is changing with position, right? So it's fastest at the equivalent position where x is 0, and it is 0 when the position is located at the end point, right? So the pendulum is like this. So it's fastest in the middle, and then at end point is smaller. So the positions v will change with respect to the position. So dv dx is describing how the position change with respect to time, right? So the equation of motion that describes how the how the velocity change with respect to position is given by this equation of motion. It's derived from the conservation of kinetic energy momentum. It's derived from the conservation of energy and momentum. Okay, so you can try to understand how this comes from, but you're supposed to learn this in your 101 or no, in 103. But anyway, I'm just giving you a few examples to remind you that these are the first order differential equation you have seen in your first year or in your whatever in your matriculations. Okay, so let's just talk about this one. So what we want to is I give you a differential equation like this, right? So this is a general situation where you have a dy dx on the left hand side. The right hand side is an expression as a function. So given this kind of situation, you want to find its solution. So what do you want when I say you want to find its solution? It means you want to know how is the y change with a x, right? So let's just read this. In order to solve a first order differential equation numerically, what we want is that we are seeking the numerical values for y equals x for all x line between intervals like this, right? So the values of x range from x1 to x2, and then the y change with respect to x through some expression like this, so that at every different values of x, you have different values of y. Tell me what are all the values of y for all the x that is lying between some intervals x1 and x2. So that is what we mean by the solution. We want to know the solutions for this first order differential equations, meaning that we want to know how this. If you know how the y change with respect to all x, then you'll be able to plot out the functions, right? So before I proceed on, we have seen this before also in the previous few lectures. For every first order differential equations, you have to provide an initial conditions. If you do not provide the initial condition, then you cannot solve it numerically. Analytically, yes. So when you solve a first order differential equations, you can solve it and you integrate it, and then the solution would be left and in terms of some function plus an arbitrary constant. So to eliminate the arbitrary constants, when you integrate over the first order differential equations, you need to provide the initial condition. So in the Python, you have to specify the values of the solutions y at one particular values of x0, where x0 is the first value in the solution space. So for example, if you were to solve an first order differentiation like this, for example, for x lying between x1 and x2, what you need is then you have to provide the values for the values of the function y when x is equals to x1, right? So here x0 meaning the first values in the solution space. The solution space here is the range between x1 and x2, and then if you don't have these initial conditions, then you will not be able to obtain the numerical solutions. Okay. So to solve the first order differential equations in Python, you use this package called ODE-INT. ODE stands for ordinary differential equations. INT means integration. So I think this is an package which is contained inside the scipy.integrate. Now we have used scipy.integrate before, right? So I think we have mentioned that earlier on, maybe one of the two examples in earlier part, where we use it for integrations. But here, we are not using the scipy.integrate for integration, but for solving differential equation. Remember, when do we use a scipy.integrate? We use scipy.integrate.quad, QUAD, to integrate some function, remember? So scipy.integrate also allows us another function called scipy.integrate ODE. Okay, so I think it's like this. It is this one, scipy ODE. I think this is the one. Scipy ODE. So you have to call scipy ODE here. So you have to call and import ODE integrate from scipy.integrate. Previously for integration we just use scipy.integrate, but here we have to use this one. So this is the function that you will learn today to integrate to solve your first order differential equation. Now it would be better if I explain to you before I show you how to do the programming, the ingredient that is required to solve a first order differential equation. So you have to provide this ingredient to the Python in order to get your answer. Now what are these ingredients? So first of all, you must have a functions in which you define your differential equation, right? So in this case, for example, you want to solve this differential equation. So this information, that is expressions of the the expression for this first order differential equation has to be defined and delivered into Python. So you have to supply the forms of your differential equations to Python through a function where you define this function with a name, and usually we call this model, right? So we just, you don't really need to call this model, but as a convenience, we just call this a model. So in this function model, you would define your equations. Now this model has basically needs two input. So you have to specify what is a symbol you use to represent the variable you want to solve for. So I call this that var. And then this t is just the independent variable. Now, I have to remind you very carefully, if you have a function like this, y equals fx, you have to distinguish between two variables, like the y and x. We have talked about this repeatedly in ZCE 110. So most of you have gone through my ZCE 110 class. I keep on saying this, and now I'm saying it again. With intentions to remind you that these are not something that you have not seen before. You have seen this. So in 110, when we first day, I think first or second lecture, when we talk about functions, when you define functions, we distinguish between the dependent variable, which is y, and independent variable x. So you have to distinguish in a function, you have a dependent variable and also independent variable. So in this case, x is an independent, y is a dependent variable. So if you have this differential equation, you have to distinguish what are the symbols for the dependent variable and what are the symbols for the independent variable. So in this case, x is the symbol for the independent variable, and you want to know what is y. So in this case, y is your dependent variable. So in order to define your differential equation, you have to tell the model what is the symbol that you use for your dependent variable and what are the symbols that you use for the independent variable. So if you were to define, say, these functions, this first order differential equation into a model, then what goes into the first argument here, that var refers to dependent variable, is y, right? So this will refers to the independent variable, which we call in this case x. So in this case, x is an independent and y. So if you cannot make a distinguish between independent variable and dependent variable, then you have a hard time. So remember, when you define your differential equation in the model, the first position is the symbol. Is the dependent variable. Second is independent variable. So in this case, this will be the y symbol. This will be the x symbol. Okay. Okay. So there's an error. Let me correct this. So I save it. Okay. Run it again. Now I have made some corrections to my scripts here. Okay, maybe not. No, you can't see my correction because I'm using another versions. So I'm using a version which is slightly different than yours. So when I make my correction, you don't see your correction on your screen. But just a minor correction, I think should be fine. Okay, so you have to define your differential equation in your model function. So in your model functions, you have to know how to do it. So we'll come to this again. So basically, in your model function, you have to define what is the dy dx. No. Okay, so let me say it again. In order to solve the first order differential equations in Python using ODE integrate, you have to generate the expressions for the first order differential equation in the model, right? So this is the model. So what you need is that when you call this model, you will return the expressions for the first order derivative. Okay, so for example, if you want to say, for example here, so the first order differential equation here is that x times y plus 6. So so in this example, if I were to do that, then this will be y times x times dependent variable. Now I think this is not a good example. So this is just an example which is slightly different than this one. It's not really referring to this example. Okay, so don't get confused. Let me say it again. So this is an example I try to give you, but in this example, it's not defining this. Okay, it's not. It's something else. So I'm just telling you that this is what you will see in the definitions of a model, right? So this is just an example. So, but finally, what you want is that you want to define the expression for dy dx. So when you call this function, the dy dx will be just a minus x. Okay, we'll come to this later on. So if this is a dy dx, dy dt equals to minus y, so the model function will return the expression of dy dx. What is dy dt? The expression of dy dt is minus x. So therefore, you define your dx dt, and then you return the values of dx dt in this. It's difficult to explain it here. It will be better if you see this in action later. Okay. Now, I'm telling you what are the ingredients that you have to provide to Python in order to perform the first order differential equation. First of all, is the expression in the model where you would return the differential equations. Then, after you have defined your differential equation, then you have to call the ODE function. You call the ODE function, then you say, ODE function, my differential equation is contained in the model. So you would define the model, then you call the ODE out, then you tell the ODE the name of the model function. In this case, the model function is just model, okay? And then you just say model. If you do not define your differential equation as model, say you call this whatever, say ABC, then you just call ABC here lah. So this name and this name is has to tally lah. Okay, so you tell the ODE integrate. Okay, say you have to tell the ODE basically 3 very important information. So in order to use the ODE solver, you say, okay, ODE solver, my differential equation is in the model. Now, other than that, you also have to tell the ODE solver what are the initial conditions for the dependent variable. Right, so you have to provide the initial conditions. I mentioned, right, first order differential equations, you need to provide one initial conditions. If you are solving second order differential equation, you have to provide 2, right? So you have to provide this information into the ODE solver. ODE integrate is our ODE solver. Then you also have to provide the range of the independent variable, right? So this independent variable actually should refers to x in this case. It depends on. Now, if you are talking about this example here, then the independent variable would be x, and then you will specify what is the range of x from x1 to x2. So you have to tell these 3 information basically. The formula where you define differential equation, the initial condition, and also the range of your independent variable. Okay, so these are all the information, and this is the way how you specify the initial condition, and then this is the way how you specify the range. So for example, the range is whatever from 0 to 7.89, then this is the range that should go in here. So now let's just look at this very simple example, the Beer-Lambert Law. Say you have a example, say you have an ray that comes in initially. Before it penetrates into the skin, it has a 1 million count per second. So this count per second is a measurement of the intensity of radiation, right? So whatever radiation, this could be gamma ray, could be beta ray, whatever. Then it goes into a material where it presents a resistance of 0.1 count per meter. That means every time this gamma ray or whatever ray that goes into the medium, every meter it will cause the count to decay by proportional to 0.1. Well, anyway, this is just a constant. Right? Just simply make up the number so that we can perform this numerical consideration. This is a numerical thing. So this is the first order differential equation. Before we solve this first order differential equations, we would want to first know about the analytical solutions. Right? So if you know the analytical solution, you have expression for how the I change with Z. So finally you find that, okay, now the I change with Z through this formula, which is a solution, analytical solution to the first order differential equation. Then when you perform the numerical integration using the ODE INT, the results that you obtain should be compared with the analytical result. And if you overlap the analytical graph and the numerical graph, you should get them to agree, right? So if you have a graph, analytical, numerical, which the result tally with each other, that means you have done something wrong. Either your numerical result is wrong or analytical result is wrong, or both are wrong, right? Now these are just a numerical straight, very simple steps that shows you how you can obtain the solution for a first order differential equation. For the first order differential equation, the solution is quite straightforward. You just integrate the equations, differential equation on both sides. Right, so just throw I to the left, and then you just throw dz to the right. Then you perform the integration. When z is equals to 0, I is highest. This is the initial value. When z equals to 0, the I0 is 1 million. I think in this case this is 1 million. Then at some intermediate depth z, the values of the intensity is just Iz. So you put in this limit, then you'll be able to integrate both sides and solve. So for first order differential equation, to obtain the solution is very straightforward. Second order differential equations is more complicated. For those who have gone through the class by Dr. Hono Haslinda, where you have learned how to solve differential equation, ordinary differential equation, whatever partial differential equation, you find that for second order or higher order differential equation, solutions are much difficult to come by. So first order is easy, just integrate on both sides, you get the answer quite easily. Okay, so this is the first order differential equations. Solve it. Okay, so now let's see how you do it. So you need to import this package as usual. Then you need to define the model, you need to put in the initial condition, and then you need to supply the independent variable range, which you call the points. I think here you call it exact point. So you have to say, okay, how large you want to solve your solution, right? For this I, you have to display as a function of z, and what is the z value. So you have to first define this z point. So you have to say, okay, z is say maybe 1 from 0 to somewhere. Now, what you mean by somewhere? How far should you go by somewhere? Okay, so how far should you go? The answer is this. I think the answer is that you should look at this alpha. Right? Alpha here refers to the coefficients, and 1 over alpha, according to what is said here, 1 over alpha is the penetration depth. Right? So it means that the object, when the radiation, when it goes into some one penetration depth, P equals 1 over alpha, say alpha is 0.1, then the penetration depth would be 10, right? So it means that after the intensity drops, penetrate into the object for 10 meter, then the intensity would drop by a factor of E. E means the natural number is a 2.7 something. What is E? E is some number, I forgot. E is 2.7. I think 2.7 something. Okay. So that is the length scale of the problem. Right. So your plot for Z should be expressed in terms of how many skin depth you want to have. Right. So you don't plot say 10, 20, whatever. You should plot the length scale to be say 5 or 3 skin depth. Right? So if you know what is alpha, then you define P is as 1 over alpha, then your Z should range from 0 to say 3P. Right? So that is how you should set your range of independent variable. So you just simply set numbers, but you should set the numbers in terms of the P. Okay, so that's how I do it, right? So this is the values of Z. Initially, Z0 here refers to the first values of Z in your independent variable, and initially at Z0 the intensity is 1 million count, and the alpha, which is a constant, 0.1. So the penetration depth is defined here. Is defined as 1 over Z. So what is my thickness? So here the thickness is the range of Z I want to define. So I will express the thickness to be 4 times the penetration depth. So once I have decided that, then the range of Z, which is an independent variable, will be just a Lie space starting from Z0. This 0 is just my Z0. And then it goes to the maximum thickness, which is 4 times the skin depth, and then there will be 50 points between 0 and the skin depth. Now that would be enough, because I expect that when the penetration goes into the materials, after 1 skin depth, it would drop to 1 over E. Then if it go further another 2 skin depth, then the I naught will become I naught divided by E squared. If you go into 3 penetration depth, then it will become I naught over E power 3. So the object will just drop exponentially faster and faster, right? So after a few, maybe 3 or 4 skin depth, then the object, the intensity will just drop to closely 0, because every time it penetrates through and skin depth, the intensity will drop by a factor of 2.7, right? So if you go to like 3 or 4, then the drop will be like 2.3, 2.7 square, 2.7 power 4, 2.7 power 5. So very fast, it will just drop. This is called exponential dropping. Okay, so you define this, then you define all these whatever the functions. And then you call your IDE solve, then you plot it. Right? So when you plot the solutions, you also want to compare it with analytical solutions. So this is the analytical expression, which I define here, so that I will plot my analytical solutions, which is provided by this line, and compare the plot from this and the plot from this. Okay, so I compare, then I'll get the answer. So this is the ODE, and this is the analytical solution. Okay, now I'm saying it fast because I know people are tired. It's 4:02. I'll take a break here for maybe 5 minutes. Come back at 4:07. I'll wait for you again. Then we'll continue and see how do. Okay, so we break here at 4:07. We'll see you again here. Any questions? You just know, you can chat it or send a message to me. Okay, so break now. Okay, so this is continue to record, and I am going to do this. Okay, so minimize this. Okay, so let's come back to the class. Okay, where am I? This is part 8. Okay, so let us try to do the coding. Maybe I just open this up a little bit, just to maximize my code. To be better like this, hopefully. Okay, so I need a larger screen. Okay, so let's just try to see how you do the differential equations for this. Now, of course, I can just cut and paste from here, but maybe I will do a better job by reproducing the scripts line by line, so that you know how the process of constructing the code looks like. Okay, so let's here, I aligned. Okay, here. So I'm going to reproduce the differential equations for this problem. where am I? Okay, dy dx equals to di dz equals to minus alpha, when minus alpha is taken to be 0.1 and it has initial conditions of a million at the beginning. Okay, so I think that is what you need, right? So let us try to do this. So I'm not sure whether I can do this exactly, but I'll try to. Okay, so first of all, I define my initial conditions. So I need this number very later on, right? So then I define this number, and I define this number. These are just the initial number that then I'll decide what is my z point. So before I define my z point, as I mentioned, you have to set the z point, the length of the z, in units of the penetration depth. So I'm going to plot for penetration depth, then I generate this z. So this is just the z value. So I press a button, what I get? I print z. Okay, so that is what I get. Okay. So after that, then I have to define my function. So I have to define my functions. I have to define my model. Right? So in the model, I have to specify what is my dependent variable and what is my independent variable. And in this model, I would like to return the expression of the differential equation. So the differential equation I'm going to talk about is looking for this di dz equals to alpha z. So I want to define a model function that would return me minus alpha z, okay, which is di dz. So that is what I do. So I said my function, I define my function called model. This is my independent variable, and then my dependent variable. So now these are the symbol that is what we call a dummy. So I'm going to pass the values of dependent variable and independent variable into the model to this dummy. So this should be called I, this should be called the Z. But I'm not going to call this I, I'm not going to call this Z directly, just to avoid possible confusions. So normally this is not what we do, okay? So normally what we call this as a name, we call this dependent variable, and this called independent variable. Then only I define my Z as the dependent, the I as my dependent variable. Then the independent variable is what I call Z. Okay, that is how I do it, right? So I don't say this is Z, I don't say this is I directly. I only define I and Z. Okay, I'm going to define my Z only as what I call a local variable. So here, I and Z are local variables that is only defined within the model. Outside the functional model, I, capital Z, that is calculated within the model will not be shown. Okay. After that, then I define what is my di dz. Di dz here is just a name. Okay, so it has a name. Di dz is just a name, and this is defined to be just minus alpha times I. Okay, and Z is not used, but anyway, we just define this as Z here. So that is it. Okay, so so in order to check whether the thing is correct, so let me try to print out some number from the model. So I'm going to pass some number to the first argument, and then pass the second number to the second argument. So say here I said the variable is say I if it's say 1 million, 1E6, and then I will define the independent variable, which is a Z, the skin depth. The skin depth is say skin depth, let me say penetration. Okay, so the penetration is a number which is equals to 1 over alpha. So the penetration depth is just 10, right? So I'm going to slot in these two numbers into the model and see whether I got some return or not. Okay, none trouble. The none is because I forgot to type in return. Okay, return. See, if you don't type the return in the model, then there's nothing to return. That's why you say none. Right? So when I type in this, the model would be called, and the values of 1 million will be passed into this dummy variable, and 10 will be passed into independent variable. Then Z, which is then local variable within the model, will be assigned a number which is 10. Then the local variable I will be defined with assigned a number which is 1 million. Then dIdZ is a number which is equals to alpha times 1 million. Now where is this alpha come from? The alpha comes from the value that is defined here. So the values of alpha that is defined outside should be able to also pass into the model. So the alpha that appears here and the alpha that appears here are both the same. Okay, but the values of I and the values of Z that is being calculated within the model will not be passed outside the model. Now let me explain to you what I mean by that. So when I press the button, I expect that this will give me a number. What is a number? The number is the values of the dIdZ defined to be just alpha, which is 0.1 times I, which is 1 million. Okay, so the values of Z that is passed in is actually immaterial. Okay, so I'm expecting that this will give me a number which is minus 100,000. Okay, so minus 100,000 is the number that I expect. So that means this number is correct. So I have defined my model correctly. Now what I want to show you is that let me try to print out this number. How about print out I? Now do I get a number when I print out I? So let me make it clear. I equals to this. Now when I press the number, the button, I wouldn't get any I to be output because, as I mentioned, I that is calculated here is calculated within the model function. And here, the I is a local variable which is only limited within the function. Outside the function, you cannot see anything. So let me press this because I'm not defining I anywhere, any else. So I expect no number to be printed out. Right? So there's no number of I. How about the Z that is defined here? Right? So Z is being passed in to the model function through the values of 10. Right? So this 10 is passed into here, and then the values of Z is supposed to be equals to 10. But the Z is equals to 10 only within the model. So again, outside the model, the Z that is the values, the local variable defined within the model function will not be passed outside the function. So when I press the button also, you wouldn't get any number. The Z is, the Z that goes into here and the Z that is defined here are two different things. So I define the Z already outside. Right? So this is the Z that comes from the definition of the lin space. Whereas the Z that is defined within here is a number which is equals to 10. Right? So when I press this, the values of Z that is displayed is not the values of Z that's calculated from within the model. Right? This Z is actually coming from the Z that has already been defined from here. Okay? So the Z that you see as an output are not the Z that is inside. So I've just tried to show you that the local variable that is defined within a function that you define to DEF will not be passed outside the function. But how about alpha, right? So alpha is a variable which is defined outside here. Right? So the alpha obviously can be calculated in the model so that the output of this print is minus 10, minus 100,000. So minus 100,000 comes from minus times 0.1 times 1 million. So obviously the values of alpha is passed and defined within the model because it's already been defined outside. Right? So what I say is that the function's value alpha that is defined outside the function can be passed in the model. So when you go into the model and you calculate a number, the symbol that represents the variable that is defined outside the function, such as alpha here, could also be passed into the model. So the variable from outside can pass into the model function, but the local variable in the model function cannot be passed outside. That's what I want to tell you. Okay, so my model function is done properly. So let me go to the next part. So the next part is to define my ODE. So I have to import ODE int from SciSpy integrate. So I have already done that. So you can take a look at the help just to see how it looks like. ODE integrate. So it gives you all these functions and you have to know how to provide the function. FNC here is referring to the model that we define here. Then you have to pass the y0. The y0 here refers to the initial condition. Then this T here refers to the linear space where you want to display the solution, and then these are extra arguments that you will pass into the ODE integrate later. But at the moment, we are not going to use this argument. Okay, this argument functions is optional. So, but we're going to use these argument functions in the next exercise. Okay, so at least in an ODE, you have to pass these three numbers: the name of the function that define the differential equations, initial condition, and the linear space for the independent variable. Okay, so that's all we need. So I need ODE, and then I tell ODE what is the name of the differential equation. So ODE model. So this model, when you call it, it will return the values of the differential equation di dz. Right, so this is di dz, which is the right hand side equations on the differential equation of what we want. So this is the right hand side. So the model will give me the expressions of the differential equation di dz. Okay, so I define my di dz to be here. Okay, then after I have mentioned where is my differential equations, I have to provide the initial condition. So initial condition has to be provided in the form like this. So the initial condition is the initial condition for I, right? So I0. So initial condition is I0. So what is the value of I0? I0 is 1 million, right? So you can just say like this. I think this is one way of doing it, but you have to be very careful, right? So I0 here refers to the initial conditions. So here y0, if you read through it here, y0 is an array. So initial condition I can be a vector. So if you do not put this into an array but just put into a number, you may have some problem. Okay, so let us try to see. Later on, maybe this doesn't work. You have to put this into an array. But anyway, let us continue. Then you have to provide the linear space. The third is the linear space. So according to the instruction here, T is the linear space. So here the definition for T is this array, a sequence of time points for which to solve Y4. So this is just our Z space. So this is just a Z. So Z here is a linear space. Okay, so when I press a button, what I get? I get an array. Now what is this array? This array refers to the values of the solution of I. So this is nothing but just the I function. The I function, which is like this, right? So this is the values of I. So you print out I. It is in a vector form. Okay, so it's a column vector. This is the values of I at Z equals to 0. This is values of I at Z equals to Z0 plus delta Z. z naught plus 2 delta z, z naught plus 2 delta. So you have numbers of points of I naught at different z value. So these are the different z value, right? So these are the different z value, and then these are your solutions like this. Okay, so print out the first solutions like this, the second solutions like this, then the third solution like this third. Okay, so it looks like it's making good. So we have to now plot the functions. Okay, so be mindful that here the I naught is the initial condition that I put in. Now normally we don't do like that. Normally to specify the initial condition, we do that like initial condition. I think we do it like this. Then you put this as in a array, and then you set I naught here. Okay, so this is an initial condition that contains one symbol. Then say init condition. See if this works. Now if it works, init cond cond. If it works, then next time you just have to edit the content of initial condition, because in some more situations we would have more than one dependent variable, where you have to supply more than one initial condition. So in that case, we just have to add in the initial condition to here. So instead of editing the entry to the argument of ODE intent, we just have to add it here. Okay, so I think this should work. So what I should do is that I'm going to restart all the kernel just to make sure that my code is running on the current code, but do not depend on the previous memory. Okay, so I should clear this as well. So I should sell, and then current output all clear. So it's all clear. So let me run this panel again. Run. I got anything? Yeah, there's no error. That means things seems to be printed out correctly. So just plot z and I and see what I get. Okay, I got a problem because I forgot to say this is plt.plot. Okay, so you got a very nice curve, and then just plot the point instead of the line. So this is the curve, which looks very nice. Okay, so let me compare the function against the theoretical values. So the theoretical values that we understand it is, I think I accidentally, yeah, I think I must have already done that accidental thing, which I always done. Okay, so let me check this out. Where am I? Okay, so I think better look at this one. So this is the online version which you are seeing at the moment. The solutions to the equation is I naught exponential minus alpha z. So let me define this function and then compare it with my numerical solutions, just to make sure that everything that I see here is correct. Okay, so let me go back to my screen. Yeah, this is the one. Okay, so I have already obtained my solution. So let me do another thing. Okay, so this is it. So let me define a functions called f analytic. Okay, FAL means that this is expression which is FA will be fine. FA means that the function that is defined analytically. So it will return a variables of z, and then it would return a functions of I naught multiply with exponents of minus alpha times that, right? So this is the expressions that is expected from the Beer-Lambert Law. I naught times exponential power minus alpha z. Okay, so then I would then plot not only this, but I also want to plot a functions of z versus fa. Fa with an argument of z. Okay, then maybe I just plot it with a different thing. Then I'll have both graph plotted. Okay, so you see that both are giving me almost exactly the same expression, so which is good. Okay, let's see if I can make things clearer a bit. So here I am using 50 points between 0 and 4 times. Maybe how about 10? Will I get a better results? 10, yeah, both give me very nice results. So that's how you perform a first order differential equations. But then let us try to make things more robust. Now, robust in the sense that this is a very simple situation where we do not use the argument functions. Okay, so the argument functions, let me introduce this. Let me show it again. Help of the ODE.int. ODE.int. So we are going to make use of this argument function here, which is sometimes very useful. Right? The argument functions is the sort of like channel where you can use to pass in some independent variable into the differential equations, so that you can use this later on to make your program to be more flexible. But if you do not make use of this argument, mostly your program will still work. But if your program become more and more complicated, then it may not work. So let us try to make a little bit change to this program that I have just written here to make use of the argument. Now, what are the arguments we want to pass in? Now, we want to pass in, for example, an argument of the value, say, alpha. Right? So we want to pass in the values of alpha into the ODE.int as a local variable. Okay? So this pass is to define an value as a local variable into the ODE model. Okay, so this is what I want to do. I want to add in one more argument here, args equals to something. Then this something will be passed into, say, the something is xx. So I want to pass this argument into the model, where this model would take in some, say dummy. Okay, this dummy would be the values, which is just the argument of xx. Okay, so for example, if I want to pass in the values of alpha, okay, so I'm going to say alpha. So alpha is a number, right? So the number that is being defined from outside. So the alpha is defined to be this 0.1. So so I'm going to pass this alpha into the ODE, and then this would be a values of name called dummy, and this dummy has a value which is equals to the alpha, which is 0.1. So the value of 0.1 is passed into this dummy. So when the dummy enters the model, the dummy has a values of 0.1. Then I say my alpha is equals to dummy. Okay, so by doing that, the alpha that's defined here is a local variable. Now this alpha value in principle is independent from the alpha that I pass in here. Okay, so to make things clearer, let me do a little bit of change. Okay, so I'll call this, instead of alpha, I'll call this alpha 0. Right, so this alpha 0 is a variable, local variable defined within model, which is not at all well, this alpha 0 is not passed outside the model, but we want to pass the alpha into the model variable through this argument called dummy. And then when dummy goes into here, then alpha naught has the values of the dummy. Then when I calculate my di d0, I'll just call it like this. Okay, so that the alpha 0 that's defined here, and subsequently the di dz that's defined here, depend on the local variable alpha naught that is passed in from the dummy. So this is just a demonstrations. Maybe I don't call this dummy. I think I call this parameter 1, the first parameter. So this param 1 or dummy are just a local variable name, okay, which is defined locally for model. Okay, so let's see if this is working. So the alpha is a number. It is already been defined. Now, when I press the button, most probably it would not work. Maybe it will work, maybe it will not work. Okay, so now this is the difference, different versions of code that I do for this code. So I am using this extra argument, which is the fourth argument that would appear inside the ODE-INT. Right? So you don't have this argument, it still works. But if you have this argument, you can make use of this argument to pass extra variable into the model. Okay, so this is the model that would be passed into the param 1. So the values of alpha naught is like this. Now let's press a button. Maybe it doesn't work. Maybe it works, maybe it doesn't. Now it doesn't work. The reason is because why it doesn't work? It doesn't work because when you look at the help file, the arguments that appears here has to be a tuple. Right? So this argument here has to be a tuple. So a tuple means what? A tuple means array, well, not an array, a list. I think the tuple is just a list. Okay, right. So you cannot just say alpha is like this. You just have to say this is the alpha, which is enclosed inside a list like this. Okay, so you have to put the values that you want to pass into the arguments in the list. I think it should work. Hopefully, if it doesn't work, then I may also in trouble. Okay, it doesn't work. So what you need is you have to put it into like this. So this is a tuple with only one single variable. So I do not know why, but this is a tuple with a single value 0.1. So you separate it by this. Then here after the comma there's nothing. So this is a tuple. Okay, so it defined to be like this. Okay, so now it works. So now I have a values of alpha pass through the argument into the model. Okay, and you call this param is a local variables. The values of alpha naught is taking the values of param 1, but the values of param 1 is passed by the values of alpha through this declaration of args. So I have to assign args equals to something into the alpha in order to calculate the di dz. Now the important thing is that you try to make this model function to be totally local. Okay, so that whatever that's calculated here will not affect the values of outside. Right? Okay, so that is to demonstrate the use of passing the argument as a local variable in the model. Now this is necessary sometimes, especially when we come to use this package for solving simultaneous equations. So you haven't seen this very important. Well, maybe let's just try to make these things more complicated a little bit because this is part of our syllabus. Okay, so let me stop this and then run this again so that it's all clear. I just want to make sure that this is all running well. Run. And then I got my plot. For some reason, when I run it once, the plot doesn't show off. It has to run again in order to show it. Right. So this is a graph that is result from the ODE. So sometimes you don't call this I, you call this ISOL to indicate that this ISOL is the solution produced by ODE. So normally we would assign a name with SOL to show that this variable is calculated from ODE or from the solver. So instead of plot I, you plot I solve. Right. So now you know that this is a solution, numerical solution. This is expression from the analytical expression for this. Okay, maybe this time let's just take this away, just to make it clean up. So I have used the alpha to solve this. Now let us try to make a slight change. The plot would be a plot of say maybe like this would be better. Okay, so I plot it. Maybe I increase the numbers of point to be, instead of 10, make it to be say 50. Okay, sorry, it's just too much. Just 50 will be fine. So you can see the dot here. Okay, so let's just try to change this a little bit by plotting the solutions for the differential equations for say 5 different alpha. So you can have 5 different materials with different values of alpha instead of just one material. Then we want to know when you change the alpha from 0.1 to 0.2, 0.3, 0.4, how would that change the expressions? Okay, how would you change the behaviors? So I would like to plot 5 different graphs. Each of the graphs would have different alpha. Okay, so you have seen this very often in your tutorials. So how do you do that? Now you can do that through many ways. One way is to use the argument. Okay, so I think this is the purpose of introducing the argument. This is one of the simple way to introduce the argument. If you don't do that, then you may, well, so, okay, I think it's very simple. So, because with the way how we define alpha is here, but alpha is defined to be a number, which is like this. So, you can bring down alpha, then this is, initial condition is always the same, okay? So, this is a package, right? So, when you supply alpha equals to 0.1, then the 0.1 will be passed to the argument, and then these arguments instead will pass its value into param, and then param will pass this value to alpha naught. Then alpha naught will be playing the role of alpha to calculate the IDT in the model function. Okay, so we are like passing the values from one to another to another. You may wonder why is this so? As again, this is to provide some flexibility. You may not see the applications here, but when you have more complicated differential equations, then this may become quite simple. So let me demonstrate to you one of the applications of this. That is, you can change the values of alpha very easily. Instead of typing alpha to be like this, let's try to do this. Say you change for I, well, for alpha, in a range, say from 0.1 to 0.2, 0.5, maybe well, maybe 0.1, 0.2, 0.3, and then 0.75, for example. So maybe no, 0.3, 0.4, 0.5, 0.5. Okay, so let's try to plot 5, 4, 1, 2, 3, 4, 5. Let us plot 5 different curves for alpha. So for alpha to change from 0.1 to 0.2, 0.3, for each values of alpha, please calculate the I solution. Okay, so by doing that, the I solution will be calculated, and then it will give you I alpha. Then for each of the solution you calculate, you can try to, now let me throw this away, we are not going to plot this. So these two lines will be iterated for different alpha. Every time alpha is changed, the I solution will be generated, and then a plot will be kept. So when you finish the alpha loop, when you go outside and say plot, show, then it will show you all the plot that has been accumulated. Okay, so let's see this. Okay, so you have different lines, right? But which one is 0.1, which one is 0.2, which one is 0.3? So you just label it. So you each of these you label with some name. So what do you want to label? You want to label 0.1, 0.2. So every time when you want to label, the label will change its value. So you say, okay, alpha. So you label the alpha, then you plot show, then you don't see anything because the label is not being asked to show up. Why is the graph looks like it's slightly different? Okay, slightly different, we think because of the penetration thickness. I think the thickness has changed. 5, 4, 6. Okay, doesn't matter. Maybe I should change this to become longer. The thickness should be not 4, should be say longer. Maybe 5. Maybe 8. Okay, let's see. Okay, so that looks much better. Okay, so now the label of alpha is not shown because you have not asked it to show. So in order to show the label, you just say PLT. Say label, PLT, not legend, not label, legends, like this, then it would print out the legends. Okay, so this will show you 0.1, 0.2, 0.3. So the larger is the alpha, then the decay is more severely hampered, right? So if alpha is larger, that means the object, the radiation would dampen more seriously compared to those that is less dampened. Okay. Now let us make a better job by saying not only number, but let us not only label number. Let's say we print out the legend to be, say, alpha equals to 0.1, alpha equals to 0.2. So what you say is you put this like this, alpha. So when you put the alpha in a comma like this, then this alpha will be a string. So when you press the button, you see 5 alphas in. So this is alpha in this string. Right, so but if you throw away this one, then it's just alpha. Right, so your number. But if you want to have both alpha equals to something and a string of an event of alpha, then this is what you can do. Right, alpha. If you do like this, it doesn't work. The reason is because this will print a label which is a string of alpha equals, and then this is to add a string, right? Remember, string plus is the addition of 2 strings. Say for example, you say string 1 is just a string 1. Then if you have a string 2, then you have a string 2. But if you add this with a plus between them, you are concatenating, what we call concatenate 2 strings together, means you stick 2 strings together. Then, so this plus thing is very nice. It stick 2 strings into one single string. So if you have 2 strings, you stick 2 together. But if you stick this to say alpha, okay, so if this is alpha, well, you have to stick to a ring. So you stick to another string, say alpha. Now this would not work. The reason is because alpha on the right hand side of this plus is a number. A number cannot be concatenated together with a string, right? So you have an error because this is not a string, but it's a number. Now how do you make a number into a string? So you just say str, then you make this into a string, right? So before you make this, you say the type of alpha. So alpha in this manner is a number, right? It's a float, it's a number. But if you put it into a string str like this, then alpha become a string. Okay, so you can easily convert the alpha into a string by saying a string like this. Okay, so if alpha become a string, then this 0.5 that's printed on the screen is actually a string in an inverted comma. Then you can then concatenate alpha. The string of alpha equals to with this, right? So this is an alpha string. This is also an alpha string, but this one is a number. It appears like a number, but it's a string. So then you have this very nice string, which is expressed as alpha equals to concatenate with the string of 0.5. So you can just replace the label to be like this, right? Then you have alpha equals to 0.1, 0.2. So this is a trick to help you to plot the string. Okay, so this is a string that looks like this. Then you have different string. then you can see that see this is decaying, and for larger alpha it decay much faster. So the purple color line decay much faster, and this decay much slower. Okay, so we have learned how to solve a differential equations for this decay process quite easily. So it is all here, right? So this to plot you. This line is just to show you the depth, the penetration depth, right? So the penetration depth, at one penetration depth, the object would drops from its initial value to this value. What is this value? This is E, okay, 1 over E. So you drop from 1 unit initially to 1 unit divided by E at the penetration of 1. Now this is basically just obvious from this formula. Okay, so look at this formula here, right? So if your Z is equals to 1 penetration depth, then the 1 penetration depth is 1 over alpha. So that means this factor will become 1. So exponential of minus 1 just means that this is 1 over E. So that means when Z is equals to 1 penetration depth, then the I become I naught divided by E. Okay, so I'm just showing you that this is a very simple behavior that most of you have seen before for a decaying process or a process where the intensity would drops exponentially. Then after 1 depth, it's decayed by a factor of E. After 2 depth, it's decayed by a factor of E squared. After 3 penetration depth is divided by E power 3. Okay, so there are two graphs here. One is the graph of the absolute values of intensity, and this is the absolute values of the depth in terms of meter. Okay, so you can scale this graph by plotting, instead of the intensity, you plot the intensity in units of the initial intensity. So instead of plotting I, you plot I over I naught. So this is I over I naught. So you see the maximum is 1, and then the rest is less than that, because the I here is to be divided by the maximum of the initial values of I naught. So sometimes it is very convenient to plot, instead of the absolute value functions versus the absolute functions of the depth, you plot the ratio of the intensity divided by the initial velocity as a function of the depth in unit of how many penetration depth. Okay, so 1 penetration depth, because skin depth is 1 over alpha. So at 1 over alpha, 2 L alpha, 3 L alpha. So you just plot the Z divided by P. Okay, so this is the Z, this is Z divided by P. So in this case, you sort of scale it. Scale means that you don't need to know what is the exact absolute values of Z and I, but you sort of just know the ratio. You see how the ratio drops as a function of how many depth it travels through. After travel 1 depth, 2 depth, 3 depth, then it just like this. So you can plot these functions straight line by showing this very simple line. So now this, for example, this line is a horizontal line plotted at 1 over E squared. So this is a 1. Okay, this is 1 over E squared. So you see that it's the solution meets at this line. So I'm saying that this decay process in the Beer-Lambert law is what you should be familiar with, especially for those medical physics students. Okay, so the decay process, the penetration process, all obey this decay law. There are many situations where you see a decay law process. For example, in your AC circuit also, you see that like the AC circuit, when you charge up the capacitor and if you release the, you switch off the switch, you switch on the switch, then the capacitor will just discharge. When it discharges, it discharges exponentially. So these are all the general behavior that you see from this kind of behavior where di dt is proportional to I. Okay? So that is the example. Then there's also another example that I show here. For example, let's just show how you solve this. dy dt equals to minus yt, and then you are given these initial conditions. Okay, so let's go through it very fast. So this is the dy. So you need a function of model that will returns dy dt. So you define dy dt equals to minus y plus 1 in the model function. So this is what you do, right? So you open the model functions, then you say this is my y, which is my t. Well, this should be the independent variable. This is my dependent variable, and this is a parameter I'm going to pass in. Okay, so the parameter I'm going to pass in is just 1. So I'll just show this as an example. So the parameter I'm going to pass in is just 1, assuming that there's nothing, right? So this is how I do it, right? So I said dy dt is this, then return from the model the expressions, the value of dy dt, which is just minus y plus 1 multiplied with param. Param is an additional number that I pass in to be just equals to 1. And the initial condition is y not equal to 0, so the initial condition is passed through into here. And this is a model, and this is the linear space. The linear space is from 0 to 1 to 0 to 1, and then there's 50 points between 0 and 1. Now be very careful about the initial condition. The initial condition is when t is equals to 0. So your linear space has to begin from 0, so that the first number that goes into linear space is also 0. So the number of y0 is the number of the function y at x equals to 0. Okay, so for example, let's say if you change this like this, if you change it to be say 0.5, and you put in the number, you still get solutions. This is a wrong solution. Why is it wrong solution? Because this is the solution not for the initial condition. This is a solution according to this graph. Is the initial condition is a solution with an initial condition at x equals to 0.5, y equals to 0. Okay, so this y0 is 0, right? So if you provide the linear space to begin from 0.5, it means that the initial condition is such that when x is equals to 0.5, y0 is 0. So this is totally different from what you want, right? What you want is you have to define x equals to 0, then only y is 0. So this should begin from 0. So be careful when you define the beginning of the linear space and the initial conditions, right? So it should be quite simple, lah. So you look at these functions. This is slightly more complicated. So you have to define a functions which is like this, and then you have to have this ut, which is a step function. So the step function looks something like this. So you have the step functions. So when t is below 10 is 0. When t is larger than 10, then it is a constant. So ut is actually a constant that is 0 or 1. Okay, 0 or 2 depend on the values of this independent variable t. So how do you define the differential equations like this into your ODE solve? So this is how you do it. And then this is another example. No, I think this is another example that is solving these equations, dx dt. So you are going to solve two differential equations at the same time. So dx dt equals to 3e minus t. This is dy dt equals to 3 minus 1. So these are two independent variables. With independent variable, these are two independent functions. Okay, the function of x versus t and the function of y versus t. So you can solve two differential equations which are independent from each other simultaneously. Well, these are simultaneous in the sense that it's specified as a function of t. So this is actually as a set of parametric equations. X as a function of t, y as a function of t. Now, in a way, x here and the y here are two different functions which does not couple. Now, so I would say that these are the two not really simultaneous, it's just two independent differential equations. So you can solve two independent differential equations at the same time, and these x and y are different functions. Now this is different than the next equation we're going to talk about. So in next equation we have differential equation that are coupled, so that the values of h and I and V, these are three different functions. They are coupled functions. They are not independent from each other. So be careful about these situations. Right? So you can use the ODE to solve two independent like this. You can use it to solve two first order differential equations, but each of these differential equations are independent from each other. So they are not coupled. That means whatever change to y does not have any effect on x, and any change in x does not change the values of y. So these are independent functions. But more generally, in a physics context, you often have functions that are interacting with each other. Right? So whatever change to v will cause change in I. Whatever change in I will cause change in h. So for example, this is a situation that looks like this. See, the values of h, rate of change of h, not only depend on t and h, but also depend on v. Right? The rate of change on I not only depend on I itself, but also depend on h and v. So this is a very typical example of what we call coupled differential equation. Three first order differential equations are coupled together. So these are simultaneous equations that are also coupled. Okay, so you can also solve this kind of coupled differential equations using ODE. In the ODE solver in Python. So we are going to talk about this in the next week lecture. So for this week, you have some assignment. Since I do not cover many assignments, I did not finish covering the first order differential equation. So perhaps I will have to change a little bit on your assignment. I think I've uploaded the assignment 7.8. So let us look at the assignment. Maybe you don't need to do it. Well, you don't need to finish. I think there are three questions. Three questions in this assignment. Maybe I take away one or two so that you can only solve one equations. Will do not solve three. Okay, so this is again complicated. Wait, let me go back to here. Okay, so give me 1 more minute. I'll finish our lecture. It's already 5 something, so I'm sorry to overshoot. Okay, so this is now this you cannot do because this is a coupled differential equation. So I don't teach this, so you don't do question 1. I'm going to change this later on. So maybe I think this question Q3 and question Q2. So I'm going to ask you to do this question Q2 and question Q3. So this question, I'll take it away. So wait for a while, maybe after maybe half an hour, only you go to look at this assignment. So assignment 8 originally contained 3 questions, but I'm going to take away this question 1. We are going to cover the coupled differential equation in the next lecture, so that you do the question 1 in the next assignment. Okay, so just give me later on, give me 30 minutes, then I'll correct this assignment 8. Okay, thank you for your attendance. Today has been a, if you make good use of this lecture, you should have learned something from me for solving differential equation. Now, the challenge is not only in this. The more challenging part is not in solving first order differential equation. There are 2 challenging things. The first thing is the solution for the coupled differential equation. That is more challenging. And solving second order differential equation will be more challenging. So that's all for today. Only 22% are left behind. Anyway, you can, anyone who have missed this, you can always go to the YouTube lecture. Maybe within 30 minutes, I should be able to upload the lecture for these hours to the YouTube. Any questions? Just free to ask me to WhatsApp. Okay. So that's all for today's lecture. See you. Okay. I'll end the meeting now.